Welcome to our final unit, which starts with Chapter 16, the Milky Way Galaxy. Again, it starts with an astronomer's almanac to peruse at your leisure, and again, I am surprised at how recent so many of these discoveries are, especially after Einstein's discoveries in the last chapter, which led to special relativity. A lot of these discoveries were made in the 20th century and in the early 21st century, which we are currently living in. The material around us blocks out light from more distant objects, but there are objects outside of our own galaxy, the Milky Way. Galaxies are clustered together, and these clusters are clustered into superclusters. The more stars, nebulae, galaxies, and other features that astronomers observed in the cosmos, the more evident it became that something else dwelled in each galaxy that they could not see. Wraith-like, this dark matter was necessary because the observable matter in almost every galaxy lacked sufficient gravitational forces to keep the stars and other matter in that galaxy bound together. The dark matter, whatever it is, must provide the rest of that gravitational binding force. Without it, the stars, gas, and dust in each galaxy would disperse. As the 21st century dawned, astronomers start getting glimpses into these wraiths. However, other than that, it interacts gravitationally with matter and curved space-time like all the matter that we can observe. We still do not know the nature of dark matter. We live in the Milky Way galaxy, which looks like this: a spiraling disk around a central bulge that looks like a UFO from the side and a whirlpool from the top. In 1923, Hubble took a historic photograph of M31, then called the Andromeda Nebula. It was one of the first spiral nebulae around which controversy raged about whether or not it was part of our galaxy or part of a galaxy that was farther away. On the photographic plate, he discovered what first appeared to be a nova. Referring to previous plates on the region, he soon realized that the object was actually a Cepheid variable star. These pulsating stars vary in brightness periodically. Further scrutiny over the next several months revealed many other Cepheids. Hubble knew that he could use the characteristics of the cyclic brightness change of Cepheid variable stars to help him calculate the distance to M31 and put the Shapley-Curtis debate about whether or not we were on the only galaxy in the universe to rest once and for all. His observations of Type 1 Cepheids led him to determine that M31 is some 2.2 million light-years beyond the Milky Way. This distance proves that M31 is not a young star and planet-forming disk of gas and dust, or an open or globular cluster in our galaxy, but rather an enormous separate stellar system. A separate galaxy, M31, now called the Andromeda Galaxy, is the most distant object in the universe that can be seen with the naked eye. Similar calculations have been done for all galaxies in which Cepheids can be observed. The distances to even more remote galaxies have been determined from observations of Type 1a supernovae in them. The interstellar gas and dust almost completely obscures from view visible light emanating from the center of our galaxy. Visual photons from there are mostly absorbed or scattered before they reach us. Therefore, Herschel, who saw only a constant distribution of stars and conclude that the sun was at the center of the galaxy, was seeing only nearby stars, and he measured the apparent magnitudes that were dimmer than they would have been had they been no interstellar gas and dust. Without adjusting for these effects, he concluded that the stars were farther away than they really are. He also had no idea of the true size of the galaxy and could not see the vast numbers of stars located in general direction of the galactic center that are held hidden by gas and dust. Because interstellar gas and dust is concentrated in the plane of our galaxy's disk, the absorption of starlight is strongest in those parts of the sky covered by the Milky Way. Above or below the plane of the galaxy, our view is relatively unobscured. Knowledge of our true position in the galaxy eventually came from observations of globular clusters. Shapley used the period luminosity relationship for Cepheid variable stars to determine the distance to the then known 93 globular clusters in the far sky. From their directions and distance, he mapped out the distribution of these clusters in three-dimensional space. By 1972, Shapley had discovered that the globular clusters are located in a spherical distribution centered not on us, but on the center of the galaxy. To see into the dust-filled plane of the Milky Way, astronomers use radio wave, infrared, X-ray, and gamma-ray telescopes, or non-visible telescopy. Photons of these wavelengths are scattered much less by the interstellar gas and dust located throughout the galaxy's disk than our visible or ultraviolet wavelengths. Observations of the distant parts of the galaxy were first made using radio telescopes. Radio waves penetrate Earth's atmosphere, so we can observe them anywhere that we can build a radio telescope, whereas infrared observations must be made at high altitudes or in space, and X-ray or gamma-ray observations are almost always made in space. We are able to tell the distance of different objects from us that are in the same line of sight by looking at for a specific photon wavelength of 21 centimeters, which is caused by the transition from electron that's spinning one way to the transition of an electron that's spinning in an anti-parallel or opposite direction. And by using the red shift or the blue shift or whatever shift we need, I believe it is galactic redshift, then we are able, or not galactic redshift, just general redshift, we are able to tell the difference and how fast a star that we're looking at, or an object that we are looking at, is spiraling Milky Way, and from there we are able to calculate how far away it is from us and its position along the Milky Way. Our radial map reveals numerous arched lanes of neutral hydrogen gas. If this were the overall structure of the galaxy, then the Milky Way would appear like any other observed galaxy. For comparison, the radial image of the barred spiral galaxy M83 strongly hints at a spiral structure and the emissions of neutral hydrogen from it. Indeed, the vast majority of distant galaxies we observe have spiral arms. Images of different observations were needed to improve our understanding of our galaxy's disk features. Note that the photograph of the Barrel Spiral galaxy shows arms outlined by spiral tracers, bright population 1 stars, and emission nebulae. As we saw in Chapter 13, these features indicate active star formation. If the Milky Way is spiral, then another useful way to further chart its structure and show that it has spiral arms is to map the regions of star-forming complexes filled with hot H2 regions, or hydrogen 2 regions, giant molecular clouds, and massive hot young stars in groups called QB or OB associations. The galaxy looks a little like this from our observations. It also has a magnetic field, which looks like this as we go over the galaxy, and the cause of that is not currently known. If you lived on a planet near the center of the galaxy, the galactic nucleus, you would see 1 million stars as bright as Betelgeuse appears from Earth today. The total intensity of starlight would be equivalent, from all those nearby stars, would be equivalent to 200 of our full moons. Night would never really fall. Stranger still, the galaxy around you would be filled with intense activity. Radial observations add more to the picture of the galactic center. Some of the most detailed radial images come from the Very Large Array near Socorro, near Mexico. Figure 1615A is a wide-angle view of Sagittarius A and surrounding features, including arcs of gas, at least 3 supernovae remnants, and localized radio sources. Huge filaments, such as the one labeled Arc, lie perpendicular to the plane of the galaxy and stretch 200 light-years northward of the galactic disk and abruptly arch southward towards Sagittarius A. The orderly arrangement of these filaments suggests that a magnetic field is controlling the distribution and flow of ionized gas, just as magnetic fields on the sun funnels such gas to create solar prominences. This resulting radio emission, produced by high-speed electrons that spiral around these magnetic fields, is called synchrotron radiation. Despite small size, Sagittarius A is one of the brightest sources of synchrotron radiation in the entire sky. Infrared observations also reveal that stars and gas in very rapid orbits around Sagittarius A. Something extremely massive must be holding this high-speed matter in such tight orbits around the galactic nucleus. Using Kepler's third law, astronomers calculate that 4.3 times 10 to the 6 solar masses is needed to prevent the stars and gas from flying off into interstellar space. In 2017, astronomers also observed a new signature of a new star formation occurring in the immediate vicinity of Sagittarius A. X-ray observations taken by the Chandra telescope in 2004 revealed that the galactic nucleus is also bathed in ultra-hot gases with temperatures of 100 million Kelvin. There is growing evidence that this gas is more than a single outburst, as flares of X-rays from the gas heated to this temperature have been seen erupting from the Sagittarius A since at least 2001. The largest such flare was observed in 2013, and they continue to occur. This is consistent with the fact that such hot gas needs frequent reheating as it radiates away from its energy, and therefore cools. Two mechanisms are under constant consideration to explain these flares. First is that asteroids fell toward the black hole there and are heated enough to emit X-rays before entering the black hole. The second theory is that magnetic fields in the vicinity of Sagittarius A get tangled up and then, like the magnetic fields of the Sun, untangle and release a burst of X-rays. In 2010, gamma-ray emissions in the shape of a pair of enormous bubbles were also observed, centered on the galactic nucleus, called Fermi bubbles, after NASA's Fermi Gamma Ray Space Telescope. They are between 6 and 9 billion years old. They are created as outflow from the gases surrounding the black hole at the center of the galaxy. Besides having these bubbles, our galaxy has a weak jet. This jet is much less distinct than jets like that in M87, in part because we have much less massive black holes that creates weaker outflow, and in part because there is less interstellar gas and dust in our galaxy's central region. As seen here. There is a black hole at the center of the galaxy. The duration of a measured flare indicated that the object at the center of our galaxy is no wider than 1 astronomical unit across. The only known object that compact and with such a high mass is a supermassive black hole. Observations also indicate that it is spinning very slowly, if at all, so is likely to be a Schwarzschild black hole. If the center of our galaxy is not active and bizarre enough, recent gamma-ray observations reveal positrons either falling towards or emerging from that region at a rate of quite a bit. I think it was 10 to the 24th per second. Recall that positrons have positive electric charges but are otherwise identical to electrons. The source of these positrons is still unknown. As mentioned at the beginning of the chapter, stars have been observed in a spherical distribution called the halo, which consists of 2 concentric cells centered on the galactic nucleus and extending far beyond the disk. Appearances can be deceiving. Although the brightness of the globular clusters suggests that they contain most of the stars in the halo, it appears that as many as 99% of the halo stars are isolated halo-filled stars spread all throughout the halo. The globular clusters and filled stars in the inner halo orbit in the same general sense that the stars in the disk orbit. The stars in the outer shell of the halo, first discovered in 2007, have very little metal, implying that they are among the oldest stars in the universe. Furthermore, these latter stars orbit in the opposite sense of the motion of the disk and inner halo stars. These big differences between the 2 components of the halo strongly suggest that they formed from different components of the early universe. Understanding this formation process will help astronomers develop a theory of how the Milky Way formed. As seen here, there are orbits of objects in the central bulge, orbits of stars in the disks, such as our sun, which go up and down through the center disk of the galaxy, and the globular cluster or halo-filled star orbit that goes around the galaxy. Since 1994, astronomers have observed 33 small galaxies that orbit in our galaxy's halo. The Sagittarius Dwarf and Canis Major Dwarf are named after the constellations in which their central regions lie. They have both spread widely through the halo and periodically pass through the disk of the Milky Way. These two galaxies are much smaller in in size and mass than our Milky Way, and are losing stars due to the disruption influence of our galaxy's strong gravitational attraction. Within the next 100 million years, they will cease to exist, their stars becoming part of the Milky Way. This process of a bigger galaxy consuming a smaller one is called galactic cannibalism. Computer simulations of galactic cannibalism performed in 2010 suggest that most of the halo-filled stars orbiting in the Milky Way are remnants of smaller galaxies. Our solar system is moving at about 860,000 kilometers per hour around the center of our galaxy. Just as the orbital motion of the planets keeps them from falling into the sun, the motion of the stars and interstellar clouds around the galactic center keeps these bodies apart. If the stars and interstellar clouds in our galaxy were not in orbit, their mutual gravitational forces would have caused them to fall together and form one massive black hole billions of years ago. Just as detecting the positions of the stars and clouds has been difficult, so too has been measuring their orbital motions. Observations show that the sun's distance from the center of the galaxy varies very little through its orbit. About 80% of the stars in our neighborhood have similarly shaped orbits. The other 20% have stars that are either taking them outwards from the center or inwards towards it, including at least 24 nearby stars moving outward with enough speed to leave the galaxy forever. The fastest of these exiting so-called hypervelocity stars is moving outward at a speed of 3.2 million kilometers per hour relative to the center of our galaxy. By combining the true speed of the sun with the relative speed of the stars around us as measured by radio astronomers, we can also determine the actual orbital speeds of stars. This computation gives us the rotation curve of the galaxy, a graph that shows the orbital speeds of stars and interstellar clouds at various distances from the center of the Milky Way. If it were only Keplerian and there were no mass outside of the galaxy, then it would follow the red dashed line. However, it actually follows the blue line, which means that there is some unaccounted for mass in the galaxy or outside of the radius of the galaxy. According to Kepler's third law, out beyond the bulk of the galaxy's visible disk, the orbital speeds of stars should decrease with distance from the galaxy's center, just as the orbital speeds of the planets decrease with increasing distance from the sun. Observations reveal, however, that galactic orbital speeds continue to climb well beyond the visible ledge of the galactic disk. Thus, there must be a presently unidentified source of gravitational force in the galaxy acting on the distant stars and clouds. These observations led astronomers to calculate that a surprising amount of matter must lie lie beyond the bulk of the visible matter, that is, the stars, gas, and dust in the galaxy. Nearly 90% of the mass in our galaxy has yet to be identified. If we include this mass, the Milky Way's total mass must be about 1.7 times 10 to the 12 solar masses. To make matters even more mysterious, much of this mass is in the form of dark matter. However, dark matter is none of it can show up on images at any wavelength. Given its gravitational effect on the stars and the gas in the galaxy we can detect, astronomers deduce that this dark matter is spherically distributed all around the galaxy in a massive halo, extending at least 12 times farther from the galactic nucleus than we are, far beyond the halo defined by the visible globular clusters and halo-filled stars. The nature of dark matter has yet to be determined. The unidentified matter in our galaxy is sometimes called the missing mass. This is a poor name because matter is not missing, we just do not know its nature.